In our last lesson, we began our discussion of rational functions by talking about their domains and by graphing a few of them as well. In this lesson, I want to go back to more traditional algebra ideas, how to combine these rational functions using the operations of addition, subtraction, multiplication, division, and composition. First, we've already seen some ideas of simplifying rational expressions, mainly by canceling out factors from the numerator and denominator of these functions, like we did in the previous lesson. So let me look at some quick examples with you. The first one is pretty easy, and we'll talk about this cancellation idea in this example. So here's the example. Simplify 4x plus 12 divided by 9x plus 27. Okay, the key in any problem like this is to start factoring as soon as possible and factor both the numerator and denominator. If you look at the original expression, it doesn't look like there's going to be any cancellation. But once we factor, we'll see something very different. So here's the first question. What can we factor out of the numerator? Well, notice that there's a 4 in both 4x and in the 12. So let's factor out that 4, and the numerator will then be 4 times the quantity x plus 3. Now let's look at the denominator. Notice that 9 is a factor of both terms as well, both the 9x as well as the 27. And so I can factor a 9 out of those terms, and the denominator will become 9 times the quantity x plus 3. So the rational expression we started with is now 4 times the quantity x plus 3 divided by 9 times the quantity x plus 3. And now it's obvious that you can cancel that x plus 3 from both the numerator and the denominator. And once you do that, your original expression is simplified to just 4/9. Now, let's try another one of these simplification problems, because before we ever get to addition, subtraction, and so on, we need to make sure we know how to simplify these rational expressions. So here's one. Simplify 5x minus 10 divided by x squared minus 4. Now, to begin the process of simplifying, I've got to factor both the top and the bottom of this rational expression. Well, the numerator, the top, is pretty straightforward. It's going to be 5 times the quantity x minus 2. Notice that the denominator is a difference of 2 squares. So it's going to factor as x minus 2 times x plus 2. And that means that the expression we started with is the same as 5 times the quantity x minus 2 divided by x minus 2 times x plus 2. And those x minus 2's will cancel because they're multiplied on the top by 5 and on the bottom by the x plus 2. And once I cancel those x minus 2's, I'm left with 5 divided by x plus 2. And that's my final answer. Now, let's do one more of these simplification problems and see how it works. The same ideas are going to come into play again, but let's just see what we get. Simplify x cubed minus x squared minus 6x, all divided by x squared plus 5x plus 6. Now, notice that there's an x in all 3 terms of the numerator. So that x is a common factor, and it can be factored out of that numerator. And that's going to leave me then with x times the quantity x squared minus x minus 6 divided by the x squared plus 5x plus 6. Now, after a little bit of work, we should find that the numerator can be factored a bit more, because x squared minus x minus 6 is equal to x minus 3 times x plus 2. And in a similar way, I can factor the denominator. The denominator is the same as x plus 2 times x plus 3. And that means that the original expression that we started with is the same as x times x minus 3 times x plus 2 divided by x plus 2 times x plus 3. And now I see the x plus 2's that are in the numerator and denominator, those can be canceled out, and I'm left with x times x minus 3 divided by x plus 3. Now, at this point, I need to share with you a potential pitfall or error that students sometimes make. It's a very common mistake made by lots of algebra students. And so let me show you that in this example. I want you to simplify x squared plus 2x divided by 2x. Well, what did you come up with? I'd be curious to know. Sometimes students will make the following mistake, and I hope you avoided this mistake. They'll notice the 2x that's up in the numerator and the 2x that's in the denominator, and they'll cancel them immediately, and they'll be left with x squared plus 1 divided by 1, which of course is the same as x squared plus 1. But this is extremely wrong, as if there are different levels of incorrectness. It's wrong to cancel those two x's. And the reason it's wrong to cancel them, in a nutshell, is because in the numerator you have x squared plus 2x. And that 2x then is being added to the x squared. When a term like that 2x is being added to the x squared, you cannot cancel it with the 2x that's in the denominator. So the way to do this problem is actually to do exactly what we've done in the past. Go back to the original problem and factor as much as possible, and then do any cancellation that can occur. So notice in the numerator that there is a common x in both terms. X is a factor of the x squared, and x is a factor of the 2x. And so you can factor that x out of the numerator, and you'll be left with x times x plus 2 on top, divided by 2 times x. Now, the x that's in the numerator is multiplied now by the x plus 2. It's not added to it, it's multiplied to it. And the x in the denominator is multiplied with that 2. And because of that, those x's, the x on top and the x on the bottom, now can correctly be canceled. And what you're left with then is x plus 2 divided by 2. And now again, it's still tempting to see that 2 in the numerator and the 2 in the denominator and to cancel them. But they cannot be canceled because the 2 in the numerator is being added to the x, not multiplied with it. So our final answer is x plus 2 over 2. And if you tried that on your own before we worked it together, I hope you were able to manage avoiding falling into that trap. Now, here's one more trap. It's a little less common, but it still happens, and I want to point it out in terms of this simplification before we move forward. Why don't you try this one first? Simplify x divided by x squared plus 3x. Okay, we start pretty quickly by factoring that denominator. The numerator doesn't have anything to factor, and the denominator factors as x times x plus 3. When you cancel the x then from the numerator and the denominator, which is perfectly legal and fine to do, it leaves us with 1 over x plus 3. And hopefully that's what you got as your final answer, because that's correct. 1 over x plus 3. Sometimes students, when they cancel those x's on top and bottom, forget that there's going to be a 1 in the numerator, so they just say that their final answer is x plus 3, as opposed to 1 over x plus 3. So 1 over x plus 3 is the right answer. Don't write just x plus 3 as the answer. That would be very, very wrong. Okay, we've done enough now with simplification. We now need to move forward with operations on rational expressions. And so the first thing we're going to do is talk about how to add and subtract. So let's do that together with the following example. Simplify 7x minus 2 divided by 3x plus 6 plus x plus 7 over 3x plus 6. Now the first thing we have to do when we want to add two rational expressions like this is to make sure the denominators are equal. By the way, that's the same thing you have to do if you wanted to add two fractions that just involved numbers. You'd have to make sure that you had what we call common denominators. In this case, you do have the same denominator in both fractions. It's 3x plus 6. And so all you do is add the numerators together and write that sum divided by 3x plus 6. So the original problem would become then 7x minus 2 plus x plus 7, all divided by 3x plus 6. And that simplifies to 8x plus 5 divided by 3x plus 6. Now, the question you really should ask is, what happens if the denominators aren't so nice? Well, the same thing that you have to do when you're just adding two fractions that involve numbers, you have to find a least common denominator. So Let's move to a second example, this time a subtraction example, where the original two denominators are different, and let's see how we would walk through that kind of a problem. So here we go. Simplify x divided by x squared minus 9 minus x divided by x squared plus 6x plus 9. Now, the two denominators here look very different, and they are different. So the way we're going to try to figure out how to find the least common denominator is to factor each of those two denominators and just see what kind of factors they have. The first denominator is x squared minus 9, which is x minus 3 times x plus 3 because it's a difference of two squares. And the second denominator, x squared plus 6x plus 9, factors as x plus 3 times x plus 3. In other words, it's x plus 3 squared. We called it in a previous lesson something like a perfect square trinomial. Now, what does that mean we need for the least common denominator? Well, I need an x minus 3 times an x plus 3 in one of the denominators, and I have an x plus 3 squared in the other. So I have x minus 3 times x plus 3, and I also have x plus 3 times x plus 3. That means my least common denominator is going to be an x minus 3 times x plus 3 squared. So that's going to be the denominator now that I need to put into both of these portions, both of these pieces of this difference. Okay, so the original problem was x over x minus 3 times x plus 3 minus x over x plus 3 squared. The first term needs an x plus 3 on both top and bottom, and so it becomes x times x plus 3 divided by x minus 3 times x plus 3 times that extra x plus 3, which I can also write as x minus 3 times x plus 3 squared. That's the first rational expression. Then I have minus x times an x minus 3 divided by the x minus 3 times the x plus 3 squared. Remember, that second fraction needed an x minus 3 in the denominator, and if I put that x minus 3 in the denominator, I have to then multiply by it in the numerator as well. And that's why the numerator of this new version of the second fraction is not just x, but x times x minus 3. Now I have the same denominator in both fractions, and that's good. It now means I can just subtract the two numerators. Well, the first numerator is x squared plus 3x when I multiply the x times the x plus 3. And the second numerator is x squared minus 3x. And now I've got to subtract those two. And now you have to be very, very careful when you subtract the second numerator. Make sure that the minus sign gets distributed to all of the terms of the second numerator. And so what you'll have then as the combined fraction is this: x squared plus 3x minus x squared plus 3x, all divided by x minus 3 times x plus 3 squared. And when you simplify that numerator, the x squareds will cancel with one another because you're subtracting them away from each other, and you're left with 6x, all divided by x minus 3 times x plus 3 quantity squared. And you're done. So remember, when you're doing subtraction in particular, you've got to make sure that minus sign gets distributed. It's very important as you go through those subtractions that you not lose the minus signs going all the way through. Now, let's look at one last example of adding rational expressions, which, when you first see it, might look a bit confusing. Simplify 8 plus x minus 4 over x plus 2. Now, your first thought might be, wait a minute, I don't see two rational expressions there. I really only see one. Only that second portion is a fraction. What in the world do I do with the 8? Well, you know how to convert 8 into a fraction. It's just 8 over 1. And so what we do now is we use 8 over 1 plus that second portion, and we work from there. Now, the first thing I should do when I want to add two fractions is to figure out that least common denominator. In this case, it's going to be 1 times x plus 2, which is just the same as x plus 2. So I need to rewrite both fractions with a denominator of x plus 2, which of course isn't going to mean anything for the second fraction. It only means something for the first fraction. And once I've written them both with a denominator of x plus 2, I can simply add the numerators. So here's what we have. We have 8 plus x minus 4 over x plus 2 is the same as 8 over 1 plus x minus 4 over x plus 2, which is the same as 8 times the quantity x plus 2 over x plus 2. There I've multiplied and divided by an x plus 2, plus the x minus 4 over x plus 2. And now I can just add the two numerators, and I'll have 8 times the quantity x plus 2 plus the x minus 4, all divided by one denominator of x plus 2. Now I distribute that 8, and I have 8x plus 16 plus the x minus 4, all divided by x plus 2. And now when I combine that numerator, I'll have 9x plus 12 divided by the x plus 2. Now, you can actually stop there. The numerator, though, can simplify just a bit more because there's actually a 3 as a factor in both the 9 and the 12. So if you wanted, you could factor out an extra 3 from the numerator, but there's not going to be any other cancellation that's going to occur with those different values. So as long as you just work your way through, if you want to factor out an extra 3, you can from the numerator. And you'll be left with 3 times 3x plus 4, all divided by the x plus 2. And once you've written it in that form, you can pretty much see that there's no other cancellations, there's no other way to simplify, and so you're done. Now, let's move on to multiplication and division. We've talked about addition and subtraction. Now we need to move to multiplication and division. And first I want to look at just a very basic example of multiplying two rational expressions. Multiply negative 3 over x squared times negative 5 over 12 x to the 7th. Well, as we've seen with the multiplication of fractions that just have numbers, all you have to do here is multiply the numerators and the denominators, and then just perform any reductions that are possible. So let me suggest you try it yourself. Multiply negative 3 over x squared times negative 5 over 12 x to the 7th. Now after you've done that, the negative 3 times the negative 5 will become a 15, and that'll get divided by 12x to the 9th. Remember, one of the laws of exponents says that x squared times x to the 7th is the same as x to the 2 plus 7, or x to the 9. So I now have 15 over 12x to the 9, and notice that 15 has a 3 in it, and so does the 12. And if you pull out a 3 or factor out a 3 from both of those and cancel them, you'll be left with 5 divided by 4x to the 9th. And that's your final answer. Okay, let's look at an example where there's a little more to do as we go through the multiplication. So here's the next example I want us to look at. Multiply 3x plus 1 over 4 times 8x over 9x squared minus 1. Well, you know again that you can just multiply the numerators and the denominators if you'd like, but you're also allowed to do any cancellation from either of the numerators and either of the denominators. So in particular, when you do this product, you have 3x plus 1 over 4 times 8x over 9x squared minus 1. Notice that that 4 in the denominator of the first fraction can cancel with part of the 8, if you will, in the second one. And you'll be left with 3x plus 1 over 1 times 2x over 9x squared minus 1. But that 9x squared minus 1 can actually factor, and you should always remember factoring when you can. 9x squared minus 1 is actually a difference of two squares just kind of hiding a bit, because it's 3x minus 1 times 3x plus 1. So what you really have is 3x plus 1 over 1 times 2x over 3x minus 1 times 3x plus 1. And now the 3x plus 1 you see in the numerator of the first fraction and the 3x plus 1 that you see in the denominator of the second can cancel. And you're left with 2x over 3x minus 1. And that doesn't simplify any further. But did you notice what we did by the time we finished that example? We actually almost didn't do any multiplication. We actually spent more of our time doing canceling. And that's important when you multiply two fractions together like this. As much canceling as you can do between numerators and denominators, you should do it. And you should do it early because it'll save you from having to do a whole bunch of multiplications later on. Okay, let's do another example. Multiply 3x plus 7 divided by 5x plus 10 times the polynomial x squared plus 7x plus 10. Now, this is sort of like one of the earlier examples we did where I just had an 8 and didn't have a fraction there to start. But that's not a problem because you can rewrite x squared plus 7x plus 10 as x squared plus 7x plus 10 divided by 1. And then it will look like you have two rational expressions being multiplied together. So the problem becomes 3x plus 7 over 5x plus 10 times x squared plus 7x plus 10 divided by 1. Now you can multiply numerators and denominators together if you'd like. You could multiply the two numerators, you could multiply the two denominators if you wanted. But before you do that, just as I said a few moments ago, you should try to cancel, because by canceling, it's going to clean up the work. It's going to reduce the work, if you will. So let's start factoring and see if there's any cancellation. Well, I see from the first fraction that the denominator, 5x plus 10, is the same as 5 times the quantity x plus 2. And I also see that the numerator of the second fraction, the x squared plus 7x plus 10, can be factored as x plus 5 times x plus 2. So there's actually an x plus 2 in the denominator of the first fraction and an x plus 2 in the numerator of the second fraction. Since everything's being multiplied together, those x plus 2's can be canceled. And that's going to give me then 3x plus 7 times the x plus 5, all divided by just the 5 in the denominator after those x plus 2's are canceled. And guess what? We're done. And again, it probably doesn't even feel like we did any multiplication. The final answer is just 3x plus 7 times the x plus 5 divided by the 5. Now remember something, those 5's can't be canceled. I know it feels, it's such a temptation to cancel those 5's, but they can't be canceled because the 5 in the numerator is being added to that x. It's not being multiplied by anything. Now, one more thing before we move on. Whenever it's possible, you should always leave your answer in a factored form. Did you notice that I didn't multiply the 3x plus 7 times the x plus 5? I just left them next to each other. There's actually lots of good reasons to keep these things in factored form. For example, let's say I walked up to you and said, hey, why don't you graph 3x plus 7 times x plus 5 divided by 5? Well, since I left it in factored form, you actually can immediately tell me what the x-intercepts of that function are, because you just set 3x plus 7 equals 0 and the x plus 5 equals 0, and you would find that the x-intercepts are x equals negative 7/3 and x equals negative 5. Since I left it in factored form, we actually could do that problem really quickly. If I had multiplied everything together, I would have gotten a longer polynomial. It would have been harder to find those x-intercepts. Now, let's turn the corner and talk about another operation. So we've talked about addition and subtraction and multiplication. Now let's talk about division of rational expressions. So the first thing we need to remember about division of rational expressions is this. If you have a over b, and that's being divided by c over d, so you have one fraction divided by another fraction, it's the same as the same a over b times d over c. In other words, you want to take the reciprocal of the second fraction and then multiply instead of divide. So this is how we can convert any division problem that involves rational expressions into a multiplication problem. And this is true as long as the denominator of the first fraction is not 0, and then neither of the two pieces of that second fraction are 0 either. So division of rational expressions is basically just multiplication as long as we take the reciprocal of the second fraction. So let's look at a number of examples of this just to make sure we understand what I'm talking about. Let's divide x squared plus 13x plus 40 over x minus 4 by the fraction or the rational expression x plus 8 divided by x squared minus 16. Now, dividing by the x plus 8 over x squared minus 16 is the same as multiplying by the reciprocal. So instead of writing the problem as a division problem, I can write it as x squared plus 13x plus 40 over x minus 4 times x squared minus 16 over x plus 8. Did you see how I took that second rational expression and flipped it? I took its reciprocal and then turned the problem into a multiplication problem. Well, I just did a few multiplication examples for you. So what do we do now? Well, we factor everywhere we can find factoring, and then we cancel as much as we can. So this problem becomes x plus 8 times x plus 5 divided by the x minus 4. That's a way to write the first fraction. And then that's times x plus 4 times x minus 4 divided by x plus 8. Notice that the x plus 4 times x minus 4 comes from the x squared minus 16. Now, you're back to a multiplication problem. Do as much canceling as you can, because by canceling those terms out, you will actually remove or reduce your work. So notice that we've got some x plus 8s, one in the top and one in the bottom, and we also have some x minus 4s. Again, one in the top, one in the bottom. Those can be canceled. And what does that leave us with? It leaves us with an x plus 5 times an x plus 4 divided by 1 if you really wanted a denominator, and that's the same as x plus 5 times x plus 4, and that's your final answer. Now, why don't I suggest you try one? Divide x squared plus 10x minus 11 divided by x squared plus 12x plus 11 by the quantity x minus 1. And I'll give you a hint. Write that x minus 1 as x minus 1 divided by 1. Okay, now I've got a new twist here. I had to take that x minus 1 and rewrite it as x minus 1 divided by 1. But that's not a problem at all, because all I have to do then, by dividing by x minus 1 over 1, it's the same as multiplying by 1 over x minus 1. So I think we can go from here now by rewriting this problem in the following way. X squared plus 10x minus 11 divided by the x squared plus 12x plus 11 now times 1 over x minus 1. And once you have rewritten it as a multiplication problem times 1 over x minus 1, you then factor and cancel. And your problem then becomes x plus 11 times x minus 1 divided by x plus 11 times x plus 1 multiplied by x minus 1. Do all the canceling you can find. I see an x plus 11 there, for example, that I could cancel. I see some x minus 1s as well. And once I've done that, I'm left with 1 over x plus 1. And so my final answer is 1 over x plus 1. Now, we've done some addition, and we've done subtraction, we've done multiplication, we've done division. We could combine a bunch of those as well if we'd like. And now what I'd like to do is talk about composition of two rational functions. Now, remember that composition just means we're plugging one function into another function. That's all it means. So let's do a relatively friendly example of this, just so we can see what composition of two rational functions would look like. Let f of x equal 3x plus 1 over x plus 2, and g of x equal 5 over x. I want us to find f of g of x. So remember what I'm doing. I'm going to take g of x and actually plug it into the f function. So f of g of x is basically f of 5 over x, which means I'm plugging 5 over x in wherever I see an x in the function f. And so what I have then is the following. F of g of x equals 3 times 5 over x plus 1 divided by 5 over x plus 2. And now I can clean that up just a little and write it as 15 over x plus 1 divided by 5 over x plus 2. And now a little bit of a trick. You want to clean up both that numerator and denominator. Do it separately. And if you do them separately, you'll be able to put them together nicely. And then once you've done that, you can then put the numerator and denominator back together and do any cancellation. So let's look at the numerator first. You have 15 over x plus 1, which is the same as 15 over x plus x over x. And now, once I have those common denominators, I can just write all that as x plus 15 all over x. Now look at the denominator. You have 5 over x plus 2, which is the same as 5 over x plus 2x over x. And now you have those common denominators again. So you can write the denominator of this complex fraction as 2x plus 5 over x. So what we've done now is written x plus 15 over x divided by 2x plus 5 over x. And now you can take that divided by and flip over that bottom fraction and now multiply. And once you've done that and simplified a bit, you're going to have x times x plus 15 divided by x times 2x plus 5, Canceling those x's will give you x plus 15 over 2x plus 5, and that's f of g of x. Now, we could have also done g of f of x and worked through that. In that case, you would be plugging f into the g function, but I'm not going to do that with you today here. I'm going to suggest that you try that on your own and then do the simplification. Well, we've done a lot of examples today of operations on rational expressions, adding, subtracting, multiplying, dividing, and we've done a little bit of composition. You're going to want to continue to practice these things, especially that composition, as the algebra can get a little messy. It's all right, you'll be fine with it, but take your time as you work through these various operations because they can take a bit of work to finish up. In our next lesson, we're going to talk about a very special topic in algebra known as partial fractions.